Okay. Okay. Thanks to the organizers for having me here to talk about non-relativistic effective theories. So Abhishek has already set up this idea of non-relativistic effective theories in the last week. And in particular, he talked a lot about heavy quark effective theories. So if you have a system where the kicks obtained by the heavy quark are much smaller than the mass. For example, lambda QCD is much smaller than the B quark mass or even the charm mass. Then you can expand in P by M and get a reduction to an heavy quark effective theory where you have a situation where you don't create or annihilate heavy quarks, but only have dynamics which are small momentum changes of these heavy quarks. So he derived the HQT Lagrangian, and then he started to look at what happens if you have a system where you don't have just a single heavy quark, let's talk about NRQED. So let's say you don't have a single heavy particle, electron, but have an electron and a positron or muon, two muons in a bound state where once again the excitations are much smaller than the mass of the particle. So the Lagrangian that he wrote down has this structure. So it's I'll write schematically first, and then we'll go in more detail. So okay. So the idea is that, let's say I have a field psi describing the electron, and let's say I have a field chi describing the antimuon, so that they can form a bound state. So the dynamics is non-relativistic in that case because the coupling is weak. And so this reduction that we see here is something you saw in HQT, exactly replacing the heavy quark field with e to the power of minus I mv dot x, some h plus capital H. And this is the large piece. So a particle with velocity v. And this is the small piece that you integrated out to get these higher dimensional terms. I've allowed for the fact, for the possibility that m1 not equals to m2, so the bound state is not of the same particle. In principle, you also know that bound states are formed by E plus E minus. So in that case, m1 will be equals to. Okay. And once again, m is the large scale here. So as you can see, terms will be in higher powers of 1 upon m. So there will be terms which have 1 upon m1 square, 1 upon m2 square, which will come in. And I've not written all the 1 upon m square terms, But you can see that in addition to the terms that you just got in heavy quark effective theory, I've written down some additional terms that you didn't see before, right? These, when you wrote HQT, you just had this piece of the Lagrangian. But then I've written these terms, and I think Abhishek mentioned the role they'll play, and we'll look at them in a bit more detail. Okay, so this is the basic setup. Yes. No, so psi is just the particle. So psi would be just h here, and chi would be its antiparticle which is going. So you do e to the power of I m v dot x, and then the h tilde that comes in is. Now, in principle, of course, h and h tilde can annihilate if they are the same particles, but they do have a lifetime, so you can. There is, right? So, good. So, I've written. So this one is psi, and this one is chi. Good, good. Yes, so that is one situation when M1 not equals to M2. Right, right. So, but if I suppose say that I let M1 equals to M2, then you can even have this situation. Yeah. So this is associated with M1. Yeah, double prime, and this is associated. This one? So dV. Yeah, so we'll look at these in a bit more detail. So basically, simple idea is that this is the scalar contraction, and this is a vector contraction. So this is dV, and this is ds, scalar and vector. C is, I'll tell you why C. I've written this extra C. Okay. Good. Sorry? Good. Thanks. Okay. So now we see that, okay, so higher terms are suppressed by more powers of m, but there is one slight change of power counting that you have to keep in mind when you're looking at this system, which is not these heavy light systems that HQT talks about. So NRQED is some system like Q, so electron, positron, or muon, and so on, or heavy quark, anti-quark, if you want, for NRQCD. And the difference is that here, the kicks that Q gets are all of the order of lambda QC, right? But if you have a heavy bound state, what is the scale of kicks that you obtain, right? So this we know very well from hydrogen atom, right? So we know that, let's say if you have a E plus E minus, so positronium is essentially the hydrogen atom with reduced mass. So we know that so it has these following scales. It has some mass m associated with me. Then you have some these moving in some orbit, and one can think that there's a momentum scale associated with inverse of R, that is ME. Right. So in fact, you can think of this alpha as the velocity, so momentum is of the order of mv with v of the order. So alpha is 1/137, so it's small. So here we go. And you also have another scale which is even lower, which is m alpha square, which is associated with t square by 2m. In fact, there are two quantities of interest. So the kinetic energy and the potential. But we know from Virial theorem that both are of the same order, right? So both of them are of the order mv square, which is so now this has one implication. So let me write down the terms that I was that haven't written down yet. This is this is an important term. Once again, similar from here with appropriate signs. So let me not write them out. You can see that. Okay. So the fact that, so in HQAT, these two terms will be of the same order because they are both 1/m1. These will be suppressed by m squared, so they'll be lower in order. But here, there's a difference. So for example, this tells you about the kinetic energy of the system. I del T psi is the energy of the system. And this is, even though this looks like suppressed by 1/m, it will be of the same order. So one lesson we learned here is d0 of the order of mv square, d squared by 2m is also. Now, similarly, this looks like it's of the same order as the 1/m term. But we know that magnetic fields are small in non-relativistic systems. So in fact, the power counting that you have to take care of is A0 is of the order of mv square, but A vector is of the order of mv cube. And there is one point to note here. This I'm doing in a Coulomb gauge, which is the natural choice for these systems. But you can see this intuitively because this is like the Coulomb potential. And this is like what you would get for, this will give rise to magnetic fields. And we know magnetic fields are suppressed by a power. So in fact, the consequence is electric fields go as mv cube, and magnetic fields go as m. So yes. Yes, exactly. Hmm. Good. Very good. Yeah, good, good. So I didn't say that. So when I write this, this should be. Because it's the potential which is mv squared. Okay. Sorry. Yes. Yeah. That's good. Because there is an extra derivative. So. Yeah. So it's easiest to go from this to this. You can see that the magnetic field in a non-relativistic system is suppressed by a power of V, right? V cross B is the current which gives you the magnetic field. So you can see that B will be suppressed by a power of V, and B is del cross A. So that's why. Okay. So this basically, with this Lagrangian along with this power counting, tells you what the importance of various terms is. So for example, this one you can see when you do it carefully that the sigma dot B will give rise to spin splitting, right? So now let's try to just be a bit more concrete. So let's talk about E plus E minus system, where this positonium and we can look at what the ground state of this is. So this is really like the hydrogen atom. So it will have some state where yeah, so it will have some binding energy which is me times alpha square, and now where does this where do these higher order terms play a role? Well, we know that sigma dot B will give you a splitting between two states of this kind. So let's say I'm in the ground state with psi and L equals to some radial. So let's say n equals to 0, L equals to 0. Y 0, 0. So let's say 0L, 0M. And then there are various two combinations I can make for the spins, which is spin equals to 0, spin equals to 1. This is known as parapositronium. This is known as orthopositronium. And we can now deduce that the binding energy corresponding to these radial wave functions will be of the order of m alpha square. But the splitting between these two will be of the order of m alpha to the power. And this simply comes once you do the power counting of the magnetic field. Basically, it's coming from the fact that B is m squared V4, and V is of the order of alpha. So that just gives you alpha. It's as straightforward as that. And in fact, that's what exactly is seen. Okay. So this probably gives you a broad setup. So before I proceed to more details, let me just pause for a second and just ask whether this looks fine, and if you have any questions about the power counting or what the structure of the operator. Yeah, so basically 1 upon m just gives you the dimension. So the m cancels out and m alpha. Okay. So let's go this way. EA goes as mv square is clear, right? This is the potential energy, right? So kinetic is similar to potential due to virial theorem and mv square. Then E is the gradient of A0. So that's mv squared because that's okay, right? Because x is of the order of 1 upon. Now, the quickest intuition is that magnetic fields in the source of EB is V cross I, V cross, sorry. EB goes as Q times V because there's a velocity, only velocities will give you a magnetic field. So if I think about this ratio E upon EB, that will go as 1 upon V. So that's the extra V here. And then gradient of A is B. This is in the Coulomb gauge. So yes, so in fact, if you make a large gauge transformation, of course, it's all the scalings are gone. Now the question is there a notion of small scale, small scale transformations? So here it's a little bit difficult because there is not such a clean notion of reparameterization invariance. So I think, at least I've not seen a discussion of using a different gauge for these non-relatives. Right. Yes.
AI and they have different scaling. So in any other gauge transformation, the scaling is not relevant.
Yeah, right. Maybe, I mean, unless you do a very small gauge transformation, yeah. Order V gauge transformation, if you do, then it would be okay. Yeah, but I've not seen any study of this. I think. There might be, but I'm not seeing. Yes. Okay. So this gives a basic setup. So we can look at some properties of systems with this binding. But one thing that would be interesting to do is look at how these operators come in, and in particular, these high dimensional operators tell you about this system. Okay, so maybe one thing I'll go and say again. So you've seen the matching of this part of the Lagrangian to the QED, like QD Lagrangian, right? So you saw that these coefficients are of the order of 1 at leading order, and you can even calculate higher order corrections to these coefficients. The slightly new terms that don't descend from the QED Lagrangian directly are these terms. And one can think about how you get them from matching with the underlying theory. So let's try and look at that. So let's say these coefficients Ci that come in the bilinear terms. You saw that they are 1. And then if you do higher order in QED, you get some series like alpha square and so on. Okay. So now let's look at this DSV. And these are not there at all in QED, right? Because all the interactions are mediated by gluons or mediated by photons. And there'll be some momentum dependence to all interactions. And here, whereas here I've written these contact interactions which have no momentum dependence. So in QED, they won't be present at leading order, but I can still see that these should have the form order alpha plus order alpha square. So let me write them a little bit more carefully. So ASV. So how can we compute these coefficients? Actually, one reason to do this, I mean, okay, it tells us about the theory, but it's a nice exercise in how to match an EFT to a fundamental theory. So it has nice pedagogical motivation. So, right. So unless I now start adding derivatives, these are the only terms that I can write. So in fact, you're right that if I go to higher order, I can even have terms like psi dagger grad psi, psi dagger grad psi. But they will be suppressed by even more power. So good, that's a good question. So sigma mu nu in the non-relativistic case will just give you sigma, right? Because what will happen is that sigma mu nu was gamma nu, and then this has this form sigma mu nu. So let's say sigma ij has this form sigma k, sigma k. So they just reduce to the, so let's say if I do the particles, then I'll just get sigma k. So that's exactly this kind of. You're worried about gamma 0 I, sigma 0 I, for example, right? But sigma 0 I is just, sigma 0 is identity, so that just gives you a vector. So that also reduces to sigma. Right. So I was a bit, so I guess contract. Right. So this is where this is information is going in. So, okay, I'll answer your question. So maybe, in fact, we'll get it quite quickly. So let's, to determine these, let's try this theory with electron and muon. Let me keep them separate, and I'll tell you why I'm keeping them different and what the differences are when we get to E plus E minus. Okay, so here, let's say if I do the calculation of this amplitude, so to get these, clearly I need 4 fields, so I need a 4-point function. So I need some amplitude for, let's say, electron and muon. Okay, so let me now calculate this process in the EFT. So E in the EFT is, so it's coming from the, let's see, so I can have these Coulomb-like exchanges, and the second contribution will come from this contact interaction. And these are the only 2 contributions that give rise at this order. Of course, I can have exchanges at higher order, but at this order, these are the only. Okay. So now let's compare the situation to in the fundamental theory. 3D. So, right, good. So here, yet I have not specified the spin. So let me do that. So let me start from S1, S1 prime, S2, S2 prime. So now, depending on whether S1 prime is the same as S1, I'll get the contribution from D and other. Okay. Right? The first comes from the bilinear piece, and the second from the. And in QED, well, there is this contribution, and actually that's it basically, right? At this order, because there's really nothing else I can do in QED. So for a system like E electron mu plus, what I get is that even at order alpha, so we said that this will start at order alpha, but even at order alpha, this gives me 0. So all these D's are 0 at this. So dV. Okay. So now let's change the system a little bit. let me look at the case when I have electron scattering with electron. So E minus, E plus. So really the positonium case. Okay. So now, so maybe just one thing. So this matches with that. That you can see by just looking at the reduction. You can see the diagrams are exactly the same. Now here, QED has this contribution as before. Let me write it. But in addition, now there is an extra contribution that you can write, which is this. Okay. So for now, you can, this once again matches with this as before, but now there is some intuition that this may be related to this particular diagram. And actually, this is even more firmly grounded than a naive intuition. This is annihilation of electron. So this photon will be basically of the order of 2m0. This is a highly off-shell photon. So in fact, it's not surprising that I can shrink this, if I look at the propagator, to a contact interaction. And now we see, actually, so how am I doing on time? 20 minutes. Okay, so then I think maybe it's not worth going into how you do it. What you can see after doing the matching, that this gives you so this maybe you can do it at home. So I'll give you the main idea. So you'll have UVs. U comes with electrons and V's with positrons, and then you have to use the non-relativistic forms of these US and V that you have seen before, I think, in the first lecture. And the key thing that comes out is that the spins that, let's say S1 prime, S2, S2 prime, the spins that come on out here are in such a combination that this gives you sigma S1, S1 prime, sigma S2. Therefore, you get the contribution in the vector channel rather than in the scalar channel. Maybe it's actually not super surprising because this vertex is gamma mu, gamma mu. So the spatial components of this don't contribute. The temporal components do not contribute. The spatials do. So you have something like gamma I, and these really just give you sigma I. So that's the main intuition. Okay. So actually this simple exercise has is telling you a little bit more. It's giving you this intuition that in these annihilation processes, you have a scale which is very large compared to the theory, M. And therefore, whenever this scale appears, then you can reduce these split vertices into a point vertex. This you've seen in the standard model also, right? Below electroweak symmetry breaking, you have the Fermi interaction. Okay, so the same idea works here. And this now can be used to get somewhat more non-trivial information about this E plus E minus system. In particular, when you have contribution from annihilation. So the idea here is that this particular process can't tell you anything about the decay of positonium because can somebody tell me why this isn't giving you any decay? Simple question. So why can I not decay? So even if I have a E plus E minus, I simply can't decay to a photon from momentum conservation. It's not a deep question. Sorry, I'm not asking deep questions. Very simple things. So, but of course, you can decay to multiple photons. Okay. The key point is that once again, no matter how many photons you have, unless some soft photons in addition get emitted, these will all be occurring at scale m. And therefore, they will be corresponding to localized operators in the effective theory. So the idea is that actually, I think this Abhishek mentioned, in principle, well, within the EFT, of course, there is no notion of decay because when I wrote the EFT, I assumed that there's no creation and annihilation of psi and chi, right? All my terms preserve U1 symmetries of chi and psi, so there can not be a decay within this EFT. The decay processes are beyond the EFT. But we know of an idea of including losses in quantum mechanics, which is by putting in complex coefficients in your term. And the intuition that we gain there is that since we are talking about annihilation, the complex terms come in these contact terms because they correspond to localized processes. Okay, so exactly. Absolutely, yes, exactly. So in fact, maybe there's one thing to, since you made this point, I mean, in principle, if you think about a Fock state of a positonium, there'll be E plus E minus, but you will have contributions with soft photons. And the main point is that these contributions are suppressed by alpha. So there is a well-defined hierarchy in this. So, okay, so let me do it this way. Let me first quickly show how the imaginary parts of dV and ds give you these decay rates, and then we do the matching calculation to find these. So let's focus on the terms of interest. Is L as delta F4 equals to so the process that can be physical is E plus E minus goes to 2 photons at the very least. Maybe you need 3. Okay, and in fact, okay, I will see this. Okay, so the idea is pretty simple. So if my Hamiltonian has some has some imaginary part, then I, and that means the decay rate is given by. Okay. So, so in fact, this gamma I can actually simply calculate by imaginary delta L4. There's a minus sign because L is related to H by a minus sign. Okay, yes, okay, good. So let me step back. I was trying to separate. So the question that I want to ask, so what we discussed so far was that I can look at annihilation / decay processes by taking complex ds dv. Okay, so suppose I know that these are complex. So that means my Lagrangian has these complex parameters. Okay, given that, can I calculate the decay rate of a physical system? So what sort of physical system? The state that I would consider would be something like I have an electron. So psi creates an electron. So psi dagger creates an electron, and chi annihilates a positron. Sorry, chi creates a positron, and psi dagger creates an electron. Okay, so my state will be something like this. Okay. In fact, let me make it more concrete. Really, it will have some form, which is like d cube r1, d cube r2, some wave function times I plus r1. So that's just saying that my wave functional form tells me how the wave function looks when the electron and positron are separated by a distance r1 minus r2. So this precisely is the form of the state. Okay, and if you want to normalize it, then basically, if you want psi equals to 1, so there's a volume factor. So this implies that integral okay, so this is just a standard hydrogen-like wave function, which is normalized to 1. Okay. So given that, if I want to now calculate what the decay rate of this is, it's simply given by the matrix element, the imaginary part of the matrix element with psi psi. Okay, and this will now be so. Psi. So maybe I will be a bit more clear. So I want the Hamiltonian. So this is x. So so that's it. So my decay rate will simply be given by this particular quantity. Okay. So now let's see. So one can already see the basic idea that I can take various states. So for example, I can, here I've not written spins, but let me also write S prime, S prime. So my parapositonium will be such that phi SS prime is delta SS prime, so singlet state. And orthopositonium will be phi SS prime equals to sigma. So that's the triplet state. So the idea is that dV will tell you, imaginary part of dV will tell you the decay rate of the triplet state, and imaginary part of ds will give you the information of the decay rate of the singlet state. Okay. So now we know some things just based on symmetry, what these what we don't know what these should be, but there are symmetry constraints on this, right? So we know that the triplet state cannot decay into two photons. And the reason for this is that if I look at the parity and charge conjugation, actually parity doesn't matter, so let me just go to the main point. So the charge conjugation of the triplet state is equals to -1, while for the singlet state, it is equals to +1. So therefore, this one can go into two photons. So okay. So how much time do I have? 10 more.
10 minutes.
Okay. Okay, fine. So right. So so the para can decay into two photons because it has C+1, while this at least has to decay to three photons. So this is alpha square, this is alpha. So that is what I can get from symmetry alone. But now to get any more information, I need a detailed matching calculation. Can you ask the question again? Good. Okay. So physically, why it's happening, maybe it's not even clear to you at this point, because right now it's just coming from the fact that I have put in some complex values for my Ds, and uh, in the EFT, it's not microscopically clear why this decay is happening, right? But in principle, I have some intuition, like E plus and E minus can come close together and they can decay, right? This is basically, the process is just E plus E minus coming together and giving rise to photons, or depending on the spin, 3 photons. Uh, and and the question is microscopically in more detail how it's coming about.
I mean, decay is not a non-strategic.
Right. So this is what I was trying to emphasize. So clearly within the EFT it's not allowed, because these photons have mass m and they're not in the EFT. This is what I'm saying is that in quantum mechanics we know that loss. So these really what's happening is that decay processes are processes that will take you out of the Hilbert space of this EFT, right? That's exactly what's happening. There were modes which were not in the EFT, but some decays happen, and that's taking you out of the modes in the EFT. Okay? So in quantum mechanics, if you have such a situation, so you have a system, and there is some interaction that takes you away out of this Hilbert space. So then how do you account for that? And the way you account for that is by putting in a complex Hamiltonian, right? Because if your Hamiltonian has some complex eigenvalues, so if everything is within the Hilbert space, the H you know is the Hermitian operator, cannot have complex eigenvalues, there's no notion of decay. But it is not Hermitian. And that's exactly the reason why this decay rate will be related to imaginary part of ds and the imaginary part of d. So if ds dv are real, then it cannot happen. That's what I'm saying. So those, I cannot write that coupling within the EFT, because the photons that will come out of this process will have, they are hard photons. They will have mm, right? And when I wrote down that EFT, I already assumed that every momentum is of the order of mv, every energy is of the order of mv square. Whereas, so I cannot write it within the EFT, but I can include it within the EFT by taking complex DSDV. Decay of the 2-point function. Yes, right, decay of the 2. Yes, that's basic. Right, exactly. Yeah. Yeah, so that's what I was trying to motivate from this simpler example of this process. Here, you can see the pinching down literally, right? Because this is M, so therefore it just pinches down to a point. The non-trivial point is that even if these are on shell, but because they are hard, you can still pinch them down to to the 4-point function. That's exactly. Right. Yeah.
Those not allowing.
Yeah, I mean, it's really like, suppose you have energy levels up to like this, and you say that I'll cut off all the energy levels. And then there are processes that take you from this, in quantum mechanics, take you from this level to this level. How do you, so if you look at some spectrum like this, then you will see that the spectrum of this is not like this, but there's a width to it. And that's exactly the point that you're trying to replace a specific energy level with a energy level with a width, I gamma. And that's exactly the process. So as some of you anticipated, so okay, yeah. So now basically it boils down to the calculation of imaginary part of DVDS. And as you said, basically in the EFT, if I calculate the IA, so I want the imaginary part of the amplitude. Where electron will spin so this one is fine. Okay, so this is the 4-point function, and basically this simply gives me imaginary part IMA. And the matching is in the fundamental theory. And this, the process that gives you this is basically you want so I think I don't have time to outline, give the details. Writing the diagram is really straightforward. IA is just use the Feynman rules. There'll be propagators here, and U bar V, sorry, V bar U, U bar V, and so on and so forth. Okay, so now to get the imaginary part, what you need is to cut this diagram. And these are the cutting rules that you can use. And finally, you have to use the fact that you're working in the non-relativistic theory. So the momentum that you put in will be MP1, let's say MP2. So of course, this is not exactly m. This m plus some root m square plus p1 square, but you're working in a situation where p1 is much, much less than m. So p1, p1 prime, and p2, p2 prime. Are all much, much less than m. And you know that in this limit, my spinners, u of p, which are like, let's say is root. So this simply becomes root e plus m by s plus small terms. Similarly, v becomes e dot sigma by e plus m. So you can use these facts and the fact and some simplification, the propagator, to finally get to the main result, which is I'm just looking at order alpha square processes, so I won't get a value for the vector piece. So I know it should go as order alpha cube, which is what I need from symmetries, and you get the values for. So yeah, that now you can just calculate, substitute it here. So the final result for gamma of octet is equal to order is 0 up to this order. Gamma of singlet is equals to sorry, octet singlet. Sorry. Yeah, gamma of vector is 0 and gamma of singlet is alpha square r0 square by m square. So so what I've just done is put pi alpha square here. And now, of course, the vector goes away. And here, I have to make these contractions. So psi contracts with psi dagger, chi contracts with chi, chi dagger contracts with chi, and that forces R1 to be equals to R2. So therefore, I get my wave function at the origin. Similarly, on the left-hand side, so my rate depends on the wave function at the origin. And alpha square by m square is just this. Some factors of pi come out. And by looking at the wave functional form, this is the form that I get. Yes, so just to make this concrete. So phi SS prime R is equals to, for the singlet, delta SS prime square root of 2, some radial wave function R0, L equals to 0, N equals to 0, which depends on the magnitude of R, and Y00 R hat. So this is the form of the wave function. And when with the delta function, I get psi of 0, and therefore it depends on the radial wave function at the origin. So this really, I think this is one of the first examples of the one loop matching calculation that you've seen in this context. And you can go further. You can look at the real corrections to ds dv that are also present. But maybe I'll pause and then we can discuss more. Okay, thanks. Right, so this was chi dagger psi. So yeah, so the chi dagger psi is prime, right? So when I contract this one, I'll get delta SS1. Is it okay? So, so the term is, let's say, chi dagger psi. Let me call it S1 prime. Let me call it, no, I. Okay, and now chi contracts with the electron, so I becomes S1, and sorry, I becomes S1 prime, and this I becomes S1. So I get delta S1. And instead, if I had a sigma ij psi j, then I would get sigma. So that's. I think you are asking a deeper question, but I am missing it. Yeah, mechanically, it's just coming from contractions.
We have two different order alpha square. There is zero. And the order alpha there is
Okay. So just for 1 second. So there are a couple of things I said. So first of all, if so. Okay. So if M1 not equals to M2, then first of all, dV that we got, it was order alpha because you had this annihilation diagram. But now that's not possible if they are different. So this becomes order alpha square already. And similarly, ds was anyway 0 irrespective of equal mass or not. This should be order alpha, 0 alpha, order alpha square. So now, so this for different particles, anyway, this goes away. The second thing that happens is that the imaginary piece also goes away because you can't have the attenuation diagram. But you can have real pieces which are order alpha square. They come for both dV and ds. Alpha. Yeah, right. So basically, electron, mu. So order alpha cannot be there, but order alpha square, you can have this kind of diagram. And that gives you both dV and ds. The T channel is this one, S channel. Yeah. No, you, because they are not identical particles. It's E plus E minus, but you have T channel processes in both, and you have additional S channel processes. So there are diagrams like those sort of diagrams do contribute. Yes, yeah, exactly. It's not in. So if you are writing a theory only for the positronium, yeah, in principle, if you write a propagator, I would say it's a complex. But that we are very familiar with, right? We have seen propagators of the kind p squared minus m squared plus I gamma kind of propagators.
We are not considering one loop amplitude in the EFT because du and ds already at the alpha square.
Can you say that again? Sorry.
They are not at the one loop level.
In the EFT?
Yes, because dv and ds are already alpha square.
It's a little bit more. It's a good point. It's a bit more than that, actually. So the question is, so we have done matching where we have gone in the fundamental theory, we've gone to alpha square order, at least in the discussion. Now the question is, in the EFT, also can I go to order by order in alpha s, etc. So now the thing is that depends a little bit on the way you do the matching. So if you do the matching in, so typically what you do, I think Abhishek mentioned this also in his previous talk. So if you, in the EFT side, let's say if you have a 4-point function where you have P0, P vector, P0 prime, P vector prime, so on and so forth. So P0, of course, you can just replace by M. And now the question is, at what P prime do you match the EFT amplitude to the QED amplitude? Now, if you do the matching at P vector prime equals to 0, so static E plus E minus, just interacting with each other. So then what happens is that in the EFT, higher loop corrections don't contribute because depends on the regularization scheme. So if you use DIMREG, then all the loop integrations will be dimensionless. They don't have any dimensional full parameter. In the sense that all the momenta have been, external momenta have been set to 0. And then you'll have gradients, etc. But you'll get integrals loop integrals of the kind dp, p to the power of n. So some loop, let's say. But all the external legs have zero momentum. So then there is no scale in this integration, loop integration, and in dim reg, they'll all go to zero. So now if you use a different matching scheme, yeah, if you use a different matching scheme, then there is a question of in the EFT also you can do a multi-loop matching. Yeah, I think that is correct. There's no way out of it. It's just a simplification to use this zero momentum kind of.
Then start from 1 plus order.
So dV.
Why one? The loop was about.
Because the loop is alpha, so their amplitude is alpha. So
No.
their coefficient should be.
It's not gonna be.
No, you can't get a 1 out of it. You'll at least, at the very least, you'll get alpha. But also you don't want to match in the EFT. You don't want to use a higher order in alpha compared to the fundamental theory, right?
So if you do the one loop in the EFT, but the original coefficient should be the T level, right? I mean that's why you will get the alpha squared.
DS is order alpha.
DS already is all the order. DS is already at the very least order alpha. There's no order 1 DS contribution, right? Because we said, I think I removed it. The power series for dV is order alpha plus order alpha squared. So at tree level, scheme doesn't matter. At tree level, we found that already this was 0 and this started from alpha. And now if you do higher order, then you get other higher order corrections, but you.
Maybe let's take a break now. Come back in 15 minutes.
Maybe. Yeah.
11 o'clock. 11. Yeah.